In this lesson 6, unit 3, laws of logarithms, we're going to be looking at some of the ways that logs can be combined, added together, multiplied, subtracted, and divided, so on. So first of all, let's investigate the product law. That just means the product of two numbers, or the product of two logs in this case. We're going to be evaluating log 16 base 2 plus log 8 of base 2. Notice, which is important, that these two have the same base. If they hadn't got the same base, we wouldn't be able to add them in quite the straightforward manner as we're going to look at now. Now, if you remember, we can change this into the 16 into a 2 to the 4 and the 8 into a 2 to the 3. So really, log of 2 to the 4 to the base 2 really is equivalent to 4, and same here, this is equivalent to 3, so we get 4 plus 3 is 7. Now, that being said, we were adding two different logs here. Here we're adding actually one log. There's only one thing being logged, and that's 16 times 8. 16 times 8 is 128. And if we look at what 128 is, it's really 2 to the 7. So again, with base 2, log of 2 base 2, and we've got this exponent 7, we find that this equals 7. We can try this in a calculator by doing log of 128 divided by log of 2. So what does that mean? I mean, we can investigate the same thing over here with a base of 3. This is 3 to the 3, 3 to the 1, so 3 plus 1 is 4. Or 27 times 3 is 81, which is really 3 to the 4. So again, it equals 4. So they both have the same result here and here. We'll get to what kind of a law this really is pointing towards in a moment. But we'll look at now the quotient law. Instead of product law where we're multiplying, we're going to look at dividing here. So, investigating the quotient law. If we are subtracting two logs like this, again we're using the same ones for brevity. This is the same as above, only we're subtracting this time. So we're going to have 4 minus 3 equals 1. So basically the answer is 1. Or if we put these two numbers, the 16 and the 8, and divide each of them, but only have the one log rather than two separate logs. If we log 16 over 8 using the base 2 as above, we find that this is really 2. And we know that log 2 base 2 is 1. So we're getting the same answers here. We'll get the same answer over here as well when we subtract these two separate logs and compare it with the single log 27 divided by 3. And we can both get the answer in both cases to be 2. You might want to pause the video and just look at that. So there's actually two laws that come out of this. When we are logging a single number, actually I should read this backwards. When we have a log, two different logs, make sure it's the same base. When we're adding two different logs, then we can write this as a product of a single log. This is the product of a single log. Product of m and n. So log m plus log n can actually be written as log of m times n. For the quotient law, when you're subtracting two logs, it can be written as a division, as a single log. Okay. Now be careful, we'll get to this later, but if there was a 2 up here, for example, we'd have to bring the 2 into this. This would have to be a 2 up here. On the other hand, I'll just erase that. On the other hand, if we have 2 out front, for example, a multiplier out front, such as this, we can actually bring this up as an exponent up here, and we'd have to do that first before we actually wrote the single log. So if the 2 was up here, it would end up being n squared. This 2 would no longer be here if we brought it up as an exponent. We haven't really dealt with that as yet, but we'll see that in a future lesson. So example 1, evaluate the following using the product or quotient law. Notice we have 2 logs and they're being subtracted. They're both the same base, so we can actually use the quotient law. And so we can really write a single log with 12 divided by 3. 12 divided by 3 is 4. Remember that that really is log 2 to the 2. And if it's base 2, we know that this equals the exponent. The reason for that you'll see in a little bit, as I alluded to just above. We can bring this out front, or if it's out front we can bring it back as an exponent. So we could have written this as 2 log 2 to the base 2. We know that this is really 2 times 1 in that case. The log here being equal to the 1. So all said, log of 4 base 2 is actually 2. In this case we're adding and subtracting, so in that case we can actually, if it's a plus, we can multiply the 9 and the 8, and if it's a subtraction we can divide by 2. So these first 2 terms can be written as a single log, so log of 9 times 8, and then we have the minus the log 2. Now at this point we have 2 logs that are being subtracted. So here is the 9 times 8 as 72. Now if these 2 are being subtracted, we can use the quotient law of 72 divided by 2. 72 divided by 2 and write it as a single log. Well, 72 divided by 2 is 36. And what is 36? It's really 6 to the 2. So we've got log 6 to the 2 with a base 6, and of course this equals 2. So you might want to pause and just read through this again. Using the law of logs to write this as a single log. So there's several steps here. We can see that this could be added together using the product with 10 and 75, product law. There's a subtraction here. I would take out the brackets and write this as a negative, and this is a negative. Or we can leave it as is shown down here. We'll write the first 2 and the last 2 using the product law. So 10 times 75 is here, and 2 and the 3 can be written as 2 times 3 here. We have 2 logs now instead of 4 with a subtraction in the middle, so we can write this using the quotient. We can turn this into 750 over 6, but as a single log rather than as 2. So that's really log of 125, and they're using the base of x. So we can't actually evaluate this not knowing what x is, but it's simplified. We've written it as they asked for us to do, as a single logarithm. So if we're writing this as a single log, we can evaluate it if they tell us what x is, and in this case x is 5. So we just circumvent that. Here we can write this as log of 5 to the 3. So because this base number is the same as the 5, the answer is 3 for the exponent. Again, we can bring the 3 out front. It's going to be written, we'll see that in a moment below, as 3 times log 5 base 5, so it's really 3 times 1, or 3. Example 3, it says use the laws of logs to write this as a single logarithm. So they're all base b, notice. And these two are being added. We can take this one step at a time. We can add these two, so we get that. These two are being subtracted, so what's happened here is, this has been written straight down here. The negative 1 has actually, this negative 1 here has been factored out as a negative 1 right here. And so that this sign here becomes positive when we write it here. We don't really have to go that route, but it can be handy. So now we've got these two. We can multiply the 2 and the 3 and write as a single log, and we can multiply the 6 and the 8 and write as a single log. And then these two logs, we can write it as 6 and 48, but the subtraction means we can write using the quotient rule of 6 over 48 or 1 over 8. And if they tell us what the value of b is, for example down here b is 2, then we're writing this, and remember 8 is really 2 to the negative 3, so the answer is 3, simply because it's log 2 of base 2, these two numbers being the same. So the answer is negative 3. Another way to write this, this whole thing here, I'll just clear the screen and I'll write it a different way, is not to form the bracket, but to simply bring the first two logs together, and we will write that as log 2 times 3 with base 2, and then we'll subtract log 6. So in fact we have to divide so we've got log log b, it's actually b down here, and this is a 6, and we'll leave the log 8 till the end, but these two now can be written as log of 6 divided by 6. That's base b still. Okay, so that's those two combined, and bring down the log 8, the negative log of 8. So this is really log of 1, and so we can write that as log 1 base b. But sorry, let me just combine these two logs as a single log now. That would be, this is 1 and this is 8. We can go 1 over 8, and we get the same idea, same answer as before. Alright, example 4, the expression log x base 2 log 2x base 2 minus log x squared base 2 minus log y base 2 is equivalent to what? So we have some of these worked out, but basically you can add these two together. Any negatives, like these two negative logs, are going to be on the bottom of a quotient of a division. The positives are going to be on top. So when you think about it, if you have a single log, select the pen here, if you have a single log, and it's base 2, the positive logs, the x and the 2x, can go on top of our quotient, x times 2x, and the negative logs can go on the bottom, x squared and y. So let's see where that is. That's going to be a single log, and the tops here, that looks like 2x squared. So the x squares are going to cancel, and we'll be left with, I think, 2 over y if I'm not mistaken. Now, that's not in any of the answers. So, what does that mean? Did I get this wrong or not? Well, maybe, maybe not. So, notice how these are written. So let's take our log of 2 over y. We can write, oh, by the way, let's see the base. The base is 2. Don't forget the base. So, let's split this up again. We can split this up because it's none of these answers. So this is a quotient, can be written as 2 logs with a negative in between, like so. And we actually know that log 2 base 2 is equal to 1, and so we can write it a little bit differently. So here we have answer D. This is done in a different way, I believe, right here in this line. So you might want to also take a look at that. Example 5, determine the value of 3 log p base 2 minus 3 log q base 2 if p divided by q is 8. So it looks like we have to form this as we solve it, and when we do, we know this is actually has a value of 8. Okay, so we can factor out these 3's for one thing, because we're, well, it seems the obvious thing to do. And then we're just got log p minus log q, both to the base 2. Well, a log minus a log is a quotient with a single log, p over q, and we know therefore that p over q is 8. We can replace p over q here by 8. And again, 8 is 2 to the 3, so we can write that as 2 to the 3, and so the answer for this is 3. So 3 times 3 times 3 is 9. So investigating the power law was what I was alluding to earlier, where if we have a log like this with a multiplier out front, like a 2, the 2 can be brought up here. Well, what does this really mean? 2 times log x. It really means log x plus log x. And if we use the product law, we can write that as log x times x, or log of x squared. So the 2 that was out front has actually ended up here. Now we can prove this is the same case here. We can write 3 times log a as log a plus log a plus log a, and really using the product law, that really means a single log with a times a times a, or a to the 3. And again, the 3 has ended up here as an exponent. So there is an actual law called the power law of logs, that this can actually be written in this format here. So here it is down here for you to look at. If there's a number like n out front, it can be brought up as a power. Example 6, without a calculator, evaluate the following. So this 12 could come down front if we need it to, and I think it might be a good idea. So we can write it as 12 log 16 base 4. 16 can be written as 4 to the 2. With this log 4 base 4, it's really, we know that the answer is 2. So 12 times 2 is 24. Again, the 21 can be brought over here and written as, therefore, 21 times log 10, and because it's not mentioned, this is base 10. So log 10 base 10 is 1. 21 times 1 is the answer. Simplify the following. Again, bring the n to the front. You'll have n log 6 base 6, and that really is n times 1. We really should evaluate what's going on here with log n to the base 6. Log n to the base 6. We don't really have a value for that, except we know that in this case from previous examples that this is equal to n. So n is actually equal to our value v. Another way to look at this is basically logging both sides. In other words, forming log and then logging this side here, so getting 6 to the log n base 6. And in a case like that, with the base being, we're going to log both sides to the base 6. So I'm going to take log of v using the base 6, and I've used the base 6 here. In this situation, when both these numbers are 6, the answer is the exponent. So log n 6 is what comes here, and on the other side we've got log v base 6. So therefore v equals n. That might take a little bit of looking at before you understand what's going on there. Or you can just memorize the fact that if you have 6 to the exponent, log of whatever to the base 6, it equals this value n. Okay, so that's what's being implied over here. Really the 6 can be brought up here, and so we had this exact value right here before, and it's equal to n. Okay, so moving on to class example 7 is an example of the following logarithmic identities. So understand these identities. If you memorize them, you can use them. They're not on your data pages, so I'd suggest you memorize them. And now you can complete the assignment, and we'll see you in class.